Hello everyone, very good evening to all of you. I know that we have started our lecture a bit late. The initial times assigned was 4 o'clock, but we were busy in a very important meet, and that is why I came up a bit late, right? Hopefully I am very much audible to all of you and I'm pretty much visible also. So now I will start this third day of GOC, General Organic Chemistry, day 3. Before starting the day 3, let me give you the clarity what we have covered till now and what are we gonna to cover in our upcoming lectures. So we went for day 1. GOC day 1, we covered the general introduction, to organic chemistry. We covered IUPAC nomenclature. We also took an idea about the electronic effects. This is something that we covered on the day 1. We went to day 2, that was yesterday. So on day 2, we covered the applications of electronic effects, which is a very vast topic actually. So apart from the what applications were involved over there, we studied the stability of reaction intermediate. Then we reached to acidic and basic strength. That again was a very big topic. We also discussed about the SIR and SIP effect, which are actually observed in benzoic acid and aniline respectively. So till here we have covered these day 1 and day 2 schedule. Now as we all know that today is day 3, I will go for complete isomerism, structural plus stereo. So how are you all everyone? Yeah, hi Sashi Kumaran, hi Sheikh Rajia. Okay, let me just begin. Anyone faces any doubt, do let me know in the comment section. I will help you to solve that particular one. Yes, so now we'll come to structural isomerism and stereo isomerism, which are two types of isomerism. The very first thing that we must know is what is isomerism. Isomerism is a property of the any kind of compound. Now which right now we are discussing about the organic compound. So the organic compounds which usually have the same molecular formula but can be represented by different structure or different chemical properties, or difference in their physical properties, or difference in any kind of spatial or structural manner. So these two are called as isomers to each other, and this property or this phenomenon of existence of these compound is called as isomerism. So isomerism definition is here, and there could be two type of isomerism. One of them is called as structural, another one is called as stereo. So I'll go for every one of them individually and in very detail. I have the plenty of examples for these two. So just stay tuned and enjoy the lecture, and don't forget to like the session everyone. Now let us come to first, what is the difference between structure and stereo? Structural isomerism means you are taking such kind of example which are different from each other in their structure, and yes, physical or chemically they can be different. So not about their properties, their structures will be different. Take this idea, everyone. Example. Let us say this is a molecule and we call it dimethyl ether, and another molecule is CH3 CH2OH. Now if you compare their molecular formula, so it will be how many carbons are there? C2. How many hydrogens are 6 and O. The molecular formula for both of the cases is the same, but structure is entirely different. And not just the structure, their functional group is different, their structures are different. Now I'll give you one more example where you will not see any structural difference, but yes, there is a difference of the arrangement of particular group in 3 dimension or in space. Take this example. Take this example, everyone. We call this molecule as an alkene, and let's suppose we have hydrogen here, we have a methyl group here, we have another hydrogen here, we have methyl here. So there is no structural change over here. If I draw another kind of compound, and this compound also has the similar kind of groups attached with a carbon atom, but again you will see the difference over here is these two hydrogen or the similar groups are in same side, and now they are opposite to each other. They usually are called cis and trans, and these two differ in their physical property specifically. So these two are called as the stereoisomers. Why are they stereo? Because their structure is same. The only difference is about the compounds having the same constitution and sequence of the covalent bond, but different relative positions. Like hydrogen is adjacent to hydrogen here, hydrogen is vertically opposite to the hydrogen, diagonally opposite. So this is the difference, right? Now before starting our topic isomerism and before going in very depth from here, I would like to give you one beautiful example of degree of unsaturation. Degree of unsaturation is something that we studied in our day 1, GOC day 1. We also call it double bond index. We also call it as hydrogen deficiency. So let us come to it and let's complete this part. So degree of unsaturation has this formula, mathematical formula of degree of unsaturation, like how many molecule a particular compound requires of hydrogen to become the completely saturated alkane. So degree of unsaturation is defined as carbon plus 1 minus number of hydrogen plus halogens minus nitrogen divided by 2. I told you we do not consider sulfur and oxygen, whether they are present in the molecular formula or not. We do not consider them. So we must know that since all isomers, we all know that isomers have same molecular formula. All isomers have same molecular formula. They have same degree of unsaturation. So if two isomers have same molecular formula, they will definitely be having same degree of unsaturation, because degree of unsaturation is calculated using this formula, and we all know that this formula gives the idea of the number of carbon atom, hydrogen atom, and this is same in both of the isomers if two isomers contain the same molecular formula. So that is what we call it as degree of unsaturation. Now I will first give you this idea that what classification are we gonna to follow in this particular class. So the classification starts from here, that we will go for isomerism, and there are like 4 major categories that we will cover individually. So guys, the very first, broadly they are classified into structural and stereo. So first I'll write structural isomerism, and number 2 is stereo isomerism. This is the very first part. Right after that we have structural, will be classified under so many categories, such as, like there are so many, literally so many. These are the classifications: chain, position, functional, chain, position, functional, metamer, ring chain, and that's it, Tauto and Tauto. So these are some set of structural isomerism. I think I must take all of them as in the sequence of their priority. RC, if we take first, ring chain, Tauto, meta, functional, chain, position. Now it is fine. This is some priority order. Anyways, I'll come to it later. Stereo is further classified into two categories. One of them is called as conformational. Another one is called as configurational. Configurational further has two types. Configurational isomer also have further two categories of classification. One of them is called as geometrical. Sorry. Geometrical isomerism. And another one is called as optical isomerism. So today's lecture is gonna to be very important, and it's a big lecture because we have plenty of things to cover. But don't worry, my notes are very much self-explanatory notes. You can download these notes right from the link given in the description, and you can also join our Telegram channel where you can download these notes, which are very much self-explanatory. You just need to read them out once, and you will get to your final concept clarification. So this is what we have to cover. Let us start from structural. Structural is chain, position, functional. There are so many. So let me just start it from the very first, called as chain isomer. Believe me everyone, I'll give you one single line definition and you will be very much confident about what it is. Chain isomer means two compounds with same molecular formula, no doubt, but different number of carbon atoms in their root chain. Now take this example. Okay, our example is already given. C4H10. Why is this example given? Okay, anyways, C4H10 is butane. So guys, this is called as like N-butane, and this is called as isobutane, or this is common name, and the IUPAC name could be, this could be simple butane, this could be 2-methyl propane. So main chain over here contains 1, 2, 3 atoms, and over here 1, 2, 3, 4. So since the number of carbon atoms in the main chain are differing or different, these two are called as chain isomer. I think this is very much easy and this is very much understandable. Now we have another such example here. C5H12. C5H12 is another example. We call this compound as pentane. So pentane could be isopentane, secondary pentane, neopentane, whatever the nature of this compound, but we are gonna to take different chains. So first of all, take one example like this, and I'll give you my trick how I used to basically make these compounds. So guys, whenever you find the degree of unsaturation here, 5 plus 1 minus 12 by 2. So we are just taking this example. It's an alkane. Wherever you are finding the degree of unsaturation is 0, no doubt there is no double bond, there is no cycle, and there is no heteroatom. As we can see, this is simple hydrocarbon. So this is an alkane. So alkane, how can we go for different number of carbon chain? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Another could be just simply make these 4. So now you need to put one more carbon atom like this as a substituent. There is no option to put the carbon over here, otherwise it will become a 6-membered ring only. Sorry, 5-membered chain only. Then we have, there could be 3 also. In that way we have to apply this. So guys, these 3 have their separate names also. We call this compound as N-pentane. These all are chain isomers to each other. This is called as isopentane. This is called as neopentane. Hopefully this part is absolutely clear to all of you. each and every of these molecules, they have different number of carbon atoms in their main chain, and that is the only differential part to define the chain isomer. Now we'll directly come to position. The position is another very easy example. I am not gonna to even read this part. I'll explain this in a single line. Two isomers, two different compounds which are having same molecular formula, no doubt, and same number of carbon atom in main chain, but there is a difference of the position of the substituent, functional group or multiple bond. So take this example, everyone. Let's say there could be a different everything is written down over here, don't worry, don't panic. Take this example. So let us suppose there is a 1 2 3 and let's say here we are applying a alcoholic group OH like this, and another one is CCC like this, and here I am attaching the OH group. Can you find any difference between these two structures? Although the number of carbon atoms in main chain is 3, that is the primary condition, otherwise they will become chain isomers, but the position of OH is different. This is called as meth-eth-prop. So propane 1-ol, this is called as propane 2-ol, like this. Very simple. So anyways, we'll come to some good examples and then we'll cover what we have studied till now. Okay. 1 2 3, three options are given to us. We are supposed to give them the one is the chain isomer of what? So guys, first one, how many number of carbon atoms are there in the main chain? 5. Second one, how many number of carbon atoms in the main chain? 4. Third one also 5. So no doubt 1 and second are chain isomer to each other because of the different number of carbon atoms in the main chain. 1 and 3, first and third, are the position isomers to each other because they have just a different position of the methyl group. One it at 3, another one at 2. So it's asking chain isomer. The second is the correct answer. See how easy questions have been asked. This was a very easy question, to be honest. Another good question here. Which pair represents the chain isomer? What do you think? Which pair is representing the chain isomer? So let us just think of it. Chain isomers must have different number of carbon atoms. This has 2 atoms. This also has 2 atoms. No, they are actually position isomers to each other. And then we have N-propyl alcohol, isopropyl alcohol. I also find that N-propyl alcohol is this, isopropyl alcohol is this, and these two are position isomers, not chain isomers, because the number of carbon atoms in the main chain are the same. 2-methyl-butane and neopentane. Oh, that can be one, because 2-methyl-butane is this and neo is this. So guys, now you can take this idea. The number of carbon atoms in the main chain must differ from each other, then only they are supposed to call the chain isomer. The correct answer should be C. Hopefully this part is going very smooth, very clear to all of you. So before going to functional, let me give you one example and let's see how many of you can give me this answer. So the answer is very simple. Here we are having this. What do you call it? Chain or position? Whether they are CI or PI? Tell me. I am waiting for your answer, everyone. Whoever is watching, do let me know the correct answer. These two examples will be chain isomers or position isomer to each other. And in the similar way, I have one or more example. These are the 3 questions, and now we have to give the correct answer here. chain and position. So see, first of all, let us take this example. Second one is having different positions, but the number of carbon atoms in the main chain are the same. So these two will be called as position isomers. Number of carbon atom in main chain 3, number of carbon atom in main chain. Okay. Then it is incorrect. See, this is 1, 2, 3. We can like whatever the way you choose, number 1, number 2, number 3, main chain will be this. This is the substituent, and here 1, 2, 3, 4. Although the position of cyanide is different in both, but the numbering will go in such a way that the main chain has different number of carbon atoms, and that is why it is Ci. Now we have a similar kind of example with us, but I asked you, nobody has responded me. No problem, I'll give you the answer. Number of carbon atoms in the main chain is 3. Number of carbon atoms in the main chain will be 1, 2, 3, and it is another 4. Their molecular formulas are entirely different. These two are not isomers, neither Ci nor Pi, but yes, they are homologues to each other. These are called as homologues to each other because there is a difference of CH2 group between these two. There is a difference of CH2 group. I hope this part is very much clear now. Ricky Roy. Third is called as functional isomerism. So for functional isomerism, first of all, we must take those functional groups into account, those functional groups in our knowledge which have similar kind of formula but different chemical properties, such as alkene and cycloalkane are also considered to be functional. We can have an alkene, a cycloalkane like this and this. Both of them have the same molecular formula of C3H6. But the functional group is different. One of them is having alkene, another one is cycloalkane. Then alkylidene, alkyne, cycloalkene, alcohol, ether. Yeah, the example which we were discussing earlier. Different physical groups are there, functional groups are there, but formula will be the same. So we consider them as the functional isomers. Then we have alkane and alkene or cycloalkane. What is going on here? General formula of compound with functional group to them. Now alkane do not have any comparison with them. Alkanes are just alkanes only, but alkyne, cycloalkane, diene, these can have the same. Then alcohol and ether, aldehyde, ketone, unsaturated alcohol, cyclic ether. These are some set of examples which are very much self-explanatory. Just take an idea and I'll show you some more example. I'll give you some more example on this. So let me just take you to one example. So everybody please have a focus here. So let's say CH3, C double bond O, OH is one compound and HC double bond O, OCH3 is another compound. Now you will find that the position of hydrogen has changed, right? What is the difference between these two? But these might be having same, they are having same molecular formula, same degree of unsaturation will be there, no need to worry. But they are different functional groups because this is carboxylic acid and this one COR is ester. Is it clear, everyone? Explain again, sir. May I know what topic are we talking about? Ricky Roy. Okay, until then you people try this question. We have a question. So what are these two compounds, position or chain? Come on everyone, try this question. Two question. The second question is similar over here. You can try this question. You might see that there is a difference in the position also, there is a different number of carbon atoms also. Look at this example, 1, 2, 3, 4, 5 and one OH group is there, and this one is 1, 2, 3, 4, 5, 6, and this one is the different position. This is at 2, this is at 3. Now what is the relationship between these two? But these two are not even isomers. See, 6 carbon atoms are there, there are only 5, and complete molecular formula should be the same. No, otherwise you cannot consider them as the isomer. The complete formula of this one will become how many carbon? 5. How many number of hydrogen are there? 3 plus 2 plus 2. Anyways, this is C5H9, not 9, H11, H11OH, or and this one is C6H13OH. So these two are homologues to each other, not isomers. D. Correct, very good. Another example, another type of isomerism is called as metamerism, and metamerism is very much similar to functional also, but what we have to take into account is we must have a polyvalent group present inside the organic compound. Polyvalent group as in which can be connected through 2 or more positions, such as ether, keto, this acidotoxic kind of group, amines. These all are considered to be polyvalent functional groups, and there will be difference in the groups present either side of the group. So let us suppose this is a question that C4H10O, we need to draw the metamer. Okay, so I will explain you what metamers exactly are and how many metamers are possible here. I'll explain you, but just first take this thing and just try to find out that how much is the degree of unsaturation, whether there is a double bond in this compound, or this compound is a simple alcohol ether, or whether it's a ketone or aldehyde. Number of carbon atom plus 1 minus number of hydrogen atom by 2. So this will become 5 minus 5, 0. So that means it's a complete saturated compound, and a saturated compound will not have any double bond in it. So one compound could be this 1, 2, 3 only. Okay, now this could be one compound, this could be another compound, 1, 2, 3, 4. I think this is the only possibility, because alcohols won't give you metamers. These two are metamers. But don't do one mistake. Do not do this mistake that CH3, CH2, CH2, OCH3 and CH3, CH2, CH2, CH2OH. These two are actually functional isomers, not metamers. So only two are possible. As I can see, only two possibilities are there for the metamerism. So guys, the way we are going right now with our organic chemistry, I will probably take another month and we'll finish the complete syllabus, because as we all know, inorganic and physical has been already covered. Then we'll come to revisional part, we'll come to some PYQ series, we'll come to so many interesting things. I will also give you most expected questions that will definitely help you in your JEE Main exam. Because JEE Main is, what are you asking? Why, sir? Why? Because these two are different functional group. Because this is a functional group called as alcohol. This functional group ROR is called as ether. And among ether only we can have different type of metamer. Different alkyl group is there. Alkyl group should be different. If there is a different functional group, then they will become functional isomers, like that. Okay, try this question and then you will become very comfortable. Try this question. Are these two metamers or not? So we all know that this is a particular group we see. This is a bivalent functional group. This is the bivalent or polyvalent this is a polyvalent group, and different here R, here H, and here R, here H. Are they metamers or not? This will give you the correct answer. Whoever is asking, Ricky Roy, if you can identify the difference between these two compounds, then the previous your example or your doubt will be clear from here. The doubt you asked is the similarly mentioned here. So guys, we all know, sir, this is not about the polyvalent functional group. This is not about this bivalent functional group. This is all about what functional group is there. The very one of them is having COOH group, which is actually carboxylic acid. And here C double bond of OR, this is called as ester. Now the different functional groups are there, that is why these are not metamers. These are not metamers. Instead, they are only functional isomers. I hope now it is very much clear. So the compound which will show metamerism, what do you think? Which compound will show metamerism? So you better draw one structure, then you will take the idea. C3H6O. So C3H6O 1, 2 like this. So I don't think this can show, because even if you make this compound like this, these two are not isomers, these two are identical. These two are identical. How do you know the identical? Just number them and try writing their IUPAC name, that will be the same only. So here this is methoxy 1 and 2. This is 1 methoxy ethane. So these two are identical. So this is incorrect. C4H10O, what do you think? C4H10. No. See, this is good. These two are metamers. So this is correct. Second is good. Then C5H10 doesn't no bivalent group, no polyvalent functional group, and C3H8O. Okay, we made a mistake. This is actually C3H8, 1, 2 and 3. These two are identical. This is like this. And these two will become functional isomers, because this is ketone, this is aldehyde. So correct answer should be again second. Second is the correct answer actually. No, not fourth. Fourth is actually giving you identical compounds are there. There is no possibility of changing the number of groups in the bivalent functional group, either side of that. So now another question is JEE Main 2021 question is here, everyone. JEE Main 2021 question is here. Which one of the following pair of isomers is an example of metamerism? Where do you find the metamerism? This is no metamerism. There should be a polyvalent functional group, but this is another example of, this is a ketone, and this is called as aldehyde. So these are functional isomers, not metamerism. Okay. Yeah, but this can be, no? This is also ketone. This is correct. See, 1. So this is called as heptane 3-on, and this one is heptane 4 on. D is the correct answer. D is here correct answer. JEE Main 2020 asked this simple question exactly 3 years back. I find this question is very easy. D is the correct answer, right? Then last and final, no, not last, we have tautomers also, but actually that is not a part of isomerism, so let me call it the last only. We have the final structural isomerism here. What is this? This is ring chain. So ring chain is one of them will be ring, another will be the chain. See, one of them is ring and another one is chain. One of them is ring, another one could be chain. Either way is fine. So this such kind of examples comes under this category. Now I will give you a priority order. Sometimes what will happen, just like aldehyde and ketone we had together, aldehyde and ketone, and they two were fighting to each other whether we should take them as metamer or we should consider them as a functional isomer. So functional isomer was the answer. How? Because they follow the priority order. So the priority order is very simple, everyone, that whenever ring chain isomerism you see, so ring chain isomerism can also be considered as functional isomerism because their chemical properties are different, their functional group is different, but ring chain isomers are kept under separate category of ring chain isomers. Then we have tautomer. If something is tautomer, then tautomers are not said to be the isomers with the this structural isomer, they were separately say tautomer. Then functional isomer. If there is a tie between the two isomers, functional isomers will be the one. Between the functional and meta, we have seen this fight before. Then we have metamers. Then we have chain isomer. And then we have position isomer. Now you better learn this sequence because this sequence will give you a lot of idea about how you can approach the upcoming questions. Now you try this question once, everyone, please try it. Allow me a second and I'll come back with a hot coffee and then we'll continue. Okay, let me do this question and then I'll leave you to some good question first. These two are actually metamers to each other, no need to check anything else. These two are ethers, and then we have Tautomerism. So just read it, everyone. Please read it and then I'll give you the idea what actually this is. Read it. Yeah. So, what do you think? We are right now discussing about the tautomers, and tautomers are not even a part of isomerism. Sir, we are ready. Okay, very nice. Very good, guys. Very good. Stay ready. Not a problem. So I was telling you that tautomerism is not even an isomerism, but what it is a state of dynamic equilibrium. For an example, there is a compound called as acetone. There is a compound called as acetone. So let us suppose you are bringing acetone from the market, and you are reaching to home and you found that a small portion, a very small part of this has converted into this compound. We usually call it enol. So this is keto, this is enol, and these two are not isomers, because isomers are what? Two different compounds that have same molecular formula but different properties, but these two are coexisting with each other. So these two are actually coexisting, and that is why something that exhibit this kind of equilibrium, dynamic equilibrium, and these two are interconvertible, different chemical groups. This is called as tautomers. So this is a very unique thing that we are observing, very different from the regular isomers that we studied till now. Okay, now let me take you to what are type of tautomerism and how does it occur. What is the condition? So the condition are actually two. Well, I'm not getting, actually let me write it, the same thing. Necessary conditions for tautomerism. What are the necessary conditions for tautomerism? Number one, they all must have, there should be an electron withdrawing group, the presence of electron withdrawing group, and this electron withdrawing group looks like this, guys, X double bond or triple bond Y. So more electronegative, and this is less electronegative, like that. Okay, these examples could be cyanide, N double bond O, C double bond O, C double bond C, C triple bond C, etc. And number two required condition for tautomerism or this interconvertible to different functional groups is presence of acidic hydrogen. So presence of acidic hydrogen is generally alpha hydrogen. So presence of alpha hydrogen is also responsible. So as I told you that HC double bond O H doesn't show tautomerism. This doesn't show tautomerism. Why? Because no alpha hydrogen. But CH3 C double bond OH shows yes tautomerism. Why? Because here how many alpha H can you count? Alpha hydrogens are 0, alpha hydrogens are 3. This is your alpha carbon. Now please read this thing. And note this thing down. It's a very important part. Like, why is tautomerism happening? There should be two things. One of them is called as the presence of this group. Another is the acidic hydrogen. Once acidic hydrogen is there, then it will start moving and another form will be recovered. Next. So now I'll come to, okay, we already have covered this part. Now right after that, how many can show tautomerism? This will be decided by presence of the electron withdrawing group is present everywhere. The only thing that is absent is number of alpha hydrogen. Alpha hydrogen is 0 here. Alpha hydrogens are 3. Alpha hydrogens are 2. This is your alpha. Then if Me3 is there, this is your Me3. Because of this, there is no alpha hydrogen. So simply I'm writing this will no tauto, yes tauto, yes tauto, no tauto. Now you will do the same for others. Kirti Sri, we have already discussed this part, that what will be our flow. Right now we are in the GOC. Right after GOC we'll start with reaction mechanism, another important chapter. And reaction mechanism, later on we'll start hydrocarbons, alkyl halide, aryl halide, alcohol, phenol, ether, aldehyde, ketone, carboxylic acid, amines, biomolecules, khatam. That's it. So guys, you might be wondering, there is no alpha hydrogen, I guess. No, but there is. Anyways, I'll show you this also. We call it para-tautomerism. So guys, take this example. I'm explaining you the case of para-tautomerism. What is para-tautomerism? What happens in this compound? There is no alpha hydrogen, although this might be a hydrogen, and if it goes like this, then it will form a compound like this. Like this is not possible here, because already because this compound O minus double bond, this is sp, and sp always requires an angle of 180 degree. So this is highly unstable. This is like highly unstable. So like it will not formed. Simply it will not formed. Okay. Now take another example, such example, the similar example. This example is here, but right now I am taking one hydrogen here and similar groups are there. So guys, we all know that hydrogen present over here will not go for conjugation because two double bond will be formed consecutively in a ring, and in a ring sp hybridized carbon atom cannot come. Two consecutive double bonds cannot be formed. So what should we do? We'll take one hydrogen from this part like this, like this, like this. This conjugation is called as para-tautomerism. This case of shifting of hydrogen, acidic hydrogen, is called as para. And in fact, you will believe me that the arrow right now, the above one is in that side. That means its enol form will be higher, like more stable. So how does it look like? This hydrogen goes here, a double bond here, a single bond here, O minus, and that H, OH, this is called as phenol. Phenol, an aromatic compound, and that is why aromatic compounds are highly stable. This reaction goes in forward and it exists. I hope this part is now absolutely clear to all of you. Nobody might be feeling any doubt till here. We are going in very good direction with a good pace. Try this question. Keto-enol tautomerism is not observed in. So take this example. This is C6H5, C double bond O, C6H5. So guys, what is C6H5? C6H5 is actually benzene, phenyl group. Now you yourself check this thing. Number of alpha hydrogen are 0. This carbon is already forming two bonds. Alpha hydrogen is 0. This is the correct answer. That's it. We don't have to even think of the other examples. Every other example might be having every other example has the alpha hydrogen apart from this. So guys, till here the number of alpha hydrogen electrochemical drawing group, we specifically studied about the keto-enol. But apart from keto-enol, there exists so many other tautomerism also that we'll come to know in a single way. You know? The only important is keto-enol. The only question comes from there. We'll take an idea what else is the comes under tautomerism. So I'll give you some example. One of them is called as hydrogen cyanide versus hydrogen isocyanide. Simple to explain. This is actually hydrogen carbon triple bond N. You all know actually this is the only 1,2 shifting will take place of hydrogen, and this is the kind of 1,2 tautomerism, because from one position, it's just from one atom it is going to just second one, the one which is closer to it. Usually it takes place in 1,3 positions also. So we'll come to that. HCN. So this will acquire this negative charge, this will acquire a positive charge, and in order to this attacks on this hydrogen and forms a compound like this. Carbon, double bond nitrogen, single bond hydrogen. Nitrogen is balanced, but carbon doesn't have a complete octet here. So carbon will take a lone pair and it will form a what should I call it? Dative bond with carbon in order to fulfill the octet of carbon or make it stable like that. So hydrogen cyanide and hydrogen isocyanide is also one of the type of tautomerism. What else are there? Then we have ketoenol, the very common one. Ketoenol is very common one. So this is how you have to show. See, this is a keto group, this is alpha. So 1, 2, 3. See, this is going to 3. So this is called as 1, 3. So earlier one that we studied is called as, it's a type of 1, 2 hydrogen transfer. 1, 2 hydrogen transfer. Tautomerism. 1, 2 tautomerism. Here we have 1, 3. How? This is your electrodensity. H will be removed as H plus. Electrodensity will come here. More electronegativity will acquire it. This will become CH3. C, O minus and H, OH. Then double bond CH2. This is called as enol form because en and ol. And this form is called as keto form. So now you want to check the number from where it is going to where. Hydrogen 1, 2, 3. So it's a 1, 3 tautomerism. 1, 3 tautomerism means hydrogen shift takes place one atom to third one. Earlier it was taking to 1 or 2. This is ketoenol. Next is the nitrous acid. Also in nitro and nitrite form. Okay, let me check. Nitrous acid is HNO2. NO2. This is how it look like. It is again the similar kind of thing is there. Oxygen being more electronegative and also an example of 1, 2 tautomerism. 1, 2 tautomerism means 1, 2 hydrogen shift. So this will become O minus and then is this O minus will attack on this hydrogen and this will leave its electron density here. So it will look like this. Nitrogen is already having this. This is your OH. And you can also show it like what should I mean? Nitrite ONO. So H O N O. This is how we can do. Okay. This is also 1, 2 shift only. You can count the number of atoms from which hydrogen is going. This is 1 and this is 2. 1, 2, 2, 1, 2 tautomerism. So I'll take another examples and we'll move forward fast. Nitro and AC nitro. So nitro, AC nitro, like here so nitrous acid was there. Now nitro means a compound like CH3. Let's say this is the alpha hydrogen and connected to a nitro group like this. So guys, you all know that N double bond is a similar kind of compound. It will release its electron density like this, reaches towards the more electronegative. It will become CH2 double bond N OH and this is the same only. This is called as AC nitro and this is called as the nitro form. and this is also 1 comma 3 hydrogen transfer, or we can also call it proton transfer. Nitroso-oxime, so same, nitroso group is N double bond O, oxime group is C double bond N OH. So again 1 3, CH2 double bond N OH. This compound is called as oxime. Carbon, doubly bonded carbon with nitrogen and OH, oxime. And this exists mainly in this form only, nitro form. And I will tell you how are we gonna decide it. This will be long arrow. A long arrow is in the backward direction. Why? Because this will be known over here in keto-enol tautomerism. So guys, what you see in keto-enol tautomerism, that keto form is more stable than enol form, because C double bond O is a stable bond. It has higher bond energy. It is not easy to break down the C double bond O bond, but it can be easier comparatively to break down the C double bond C bond. So that is the only logic which is working here. Enol will be lesser stable than keto. Keto form usually be there, but there could be some conditions where keto form, enol form can win over keto, like the case I told you about para-tautomerism, where an aromatic compound was formed. So such kind of exceptional cases may help, but not very usually. So now you see the order of stability of the following tautomeric compound is, we have been given with three forms here, and we have to decide which one of them will be more stable. Three is most stable given. So tautomeric will be there, enol compound, no doubt. And we can see one more thing here. See, these three are actually resonating structures only. This is reso stable. This is keto form. And these two are the enol forms. There is a resonance also. There will be a hydrogen bonding between these two. 6-membered ring is formed. But here no such conjugation. If no conjugation, then no stability. Simple. Keto will be more dominant. Correct answer should be B. Another question. Which of the following can exhibit tautomerism? It's very easy question. So wherever we find, okay, there is no hydrogen is here. So this can go like this and can show. Here this hydrogen is also here. Here this hydrogen can also undergo like this. See, this can go like this, this can go like this can go like this. This hydrogen can also go like this, like this. Only 1 and second. Why not 3? Anyways, since there is no aromaticity here, so we should not also go with the beyond than that. Aromaticity is there, then it may allow, like we already formed taking the cyclohexyl ring there, and we formed a phenol from there, which is an aromatic compound. So just consider this only. So this can go, yes, but here no alpha hydrogen, this side and here is a hydrogen that cannot go. As I told you, sp hybridized carbon will come up. This two double bond will make a sp hybridized carbon that want to stay with the groups in 180 bond angle, and it is highly strained here in the ring, so that is why this is not possible. So correct answer should be first and second. Okay, this is JEE Main 2022 question has been asked. It is asking us which of them will be having the highest enol content. What do you think? Highest enol. So guys, do one thing. This is hydrogen. This will come like this. Make it OH. The another hydrogen is here. Goes and it will make like this. Hydrogen. A compound will come which will almost look like this. This is called as fluoroglucinol, and the most important part, this compound is aromatic and most stable. So I think this should be the correct answer. C. Next question. See, number of tautomer. So basically, number of tautomer is equals to the number of alpha hydrogen. So how many alpha hydrogen can you see? 2 hydrogen here, 1 here, 3 will be the correct answer. Which of the following will show tautomerism? Benzaldehyde will not show, I guess. Formaldehyde cannot show. Benzaldehyde cannot show. Propionaldehyde is actually this, metheth prop. This has alpha hydrogen 2, and this will show. Only C. Compound molecular formula can show. Take this thing as homework. We have already completed this part, and then we have number 2 part of this chapter, conformational isomerism. Now we have come to what? Conformational isomerism. What is the meaning of conformer? Conformers are the different type of stereoisomers which are possible because of the free rotation of carbon-carbon, or like free rotation of the sigma bond. And if a carbon which is connected to different groups, or even not, due to the free rotation only, the relative position with respect to each other changes. How? I'll show you here. So guys, let us take this example. We are picking ethane as one of the example. Ethane. We can't see the same in methane, but ethane is perfect. How should we represent ethane? Let's say this is another carbon, and this is how we are making it: hydrogen, hydrogen, and hydrogen. This is also in the same way: hydrogen, hydrogen, and hydrogen. And we all know that carbon-carbon, this is a sigma bond. Carbon-carbon sigma bond, and sigma bond does what? Free rotation. So let us say I have this rotate. I have rotated it by, let's say, 180 degree. So after rotating 180 degree, how does it look like? Let us say front carbon has been kept fixed in the similar way, back carbon will change to 180 degree. So these two different. This one was initially parallel to each other. These two are parallel to each other. Now this has come under the gap of these two. So this kind of arrangement is called as, these two are called as the conformational isomers to each other. And this arises because of what? Simple free rotation of the sigma bond. It arises because of the free rotation of the sigma bond. If there is no doubt between any kind of concept here, then I will move forward. The same thing they are explaining. Different structure generated due to the carbon-carbon rotation of single bond is sigma bond. It is an example of conformational isomerism. This is also a stereoisomerism, but one of the conformational isomer. Then before going to conformational isomerism, we must know, like, how do we represent a three-dimensional molecule in two dimension, because that will actually help us to know about the conformational isomers very well. Okay, otherwise we will not be able to see where is the position changing, which part has been moved and which one is not. So very first comes is called as wedge dash or flying bridge projection. This is something that we already have studied earlier. So carbon, these two are the planar one, coming out of the plane, going inside the plane. This is going inside or inwards the plane. This is going inwards the plane. This is coming outwards the plane, outward. These two are planar in the same plane. Bond angle is 190, 28 minute only. This representation is called as flying bridge projection. Example, check this example. Let's say I have to write ethane. So how do you present one carbon here, another carbon here, hydrogen, then with this also. This is your ethane. Number two is called as horse projection, and it looks like a horse, like horse riding. So how do we draw this structure? It's very easy. The easiest example could be ethane. So ethane, write down the formula of two individual sp3 hybridized carbon. We have to consider them sp3 only. So this is, let's say this carbon atom is your front carbon, this is your back carbon. So guys, the front carbon somehow look like this dot, and it's a projection. Projection means it might be a, see, this is the fourth bond. This is the fourth bond, and if you hide this fourth bond and try to take a projection, like one bond is held and torch has been given up to light this compound, then you will receive a triangle on the wall. Why? Because these three exist in the form of triangle only. If you hold one thing and you put a light, then it will be a triangle looking like thing. The projection will be a triangle, the shadow will be a triangle. So similarly, we are following this also. So this type of arrangement where these two are aligned with each other, now it has become, this is hydrogen, hydrogen, hydrogen. This is your back carbon, this is your front carbon, this is same hydrogen, hydrogen and hydrogen. This type of projection is called as horse projection. Seems like you saw a horse. Then if you squeeze the horse projection, it becomes the Newman projection. If you squeeze the horse projection, it will become what? So what you are doing is, let's say this was our compound initially. Initially this was the compound hydrogen, 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 front, back, hydrogen, hydrogen, and hydrogen. Now you put your eye here and try to look at this. Then what will happen? Front and back, they will hide, they will be hidden. What we are talking about? CH3 single bond CH3. We all know this is your front, this is your back. So in Newman projection, what happens? Front carbon is represented by a dot, and the 3 hydrogen atoms are there in a Y shape like this. It's also a projection. The rear or back curve is represented by a ring. Let me change the color of the ring so that it is visible. Then same groups are attached to ring. Ring also has similar type of hydrogen, hydrogen and hydrogen. So now it seems like that I am watching it from here. This is called as Newman projection. Which is actually derived from the Sohor's only, or it's like the Sohor's only. And this is called as Sohor's projection, like that. The molecule was ethane, and for ethane we have made both type of arrangements, both type of projections, and writing down a 3D molecule into 2-dimensional to understand what groups are attached there with. Now we have another topic here called as a dihedral angle. What is a dihedral angle? Dihedral angle is actually arised from here. Okay, the front one group is there, another group is there, and take their parallel lines, and the angle between them is called as dihedral angle. In any of the projection you can take it. So dihedral angle can be varied. Okay, so like take this example everyone, just like ethane I'm talking about. So initially let's say it is looking like this. So this type of structure which we are seeing, where all the hydrogens are right behind hydrogen, theta is actually 0. So let us say we have changed theta to 60 degree. So okay, keep front fix and back rotate. So rotate it. So now this is your front, so it will remain the same. But what happens at the back? They will go in the gap like this. So these two right now are different. So this is all game of dihedral angle. Dihedral angle changes, the conformation may change. This conformation is called as eclipsed. Eclipsed. This conformation is called as staggered. Eclipse versus staggered. So I have already explained this staggered and eclipsed. So guys, all the conformations other than eclipsed and staggered, like whatever the degree of rotation there, apart from this 60, 80, 90, and wherever these two are formed, apart from that, if you change it in any angle, all others are called as skew conformer. So there could be a trillion number of skew conformer, and even more, infinite number of skew conformer are possible. But the most important are the two. One of them with most strain, most unstable, that is called as eclipsed, and another one is the most stable, it's called as staggered. Then we have another term called as torsional strain. The meaning of torsional strain is the groups adjacent to each other on individually atoms, front and back atom, they repel each other. The repulsion is called as torsional strain. Very simple. The resistance towards the eclipsing of a bond. Eclipsing of a bond means one coming right behind one. Two atoms are coming close to each other, and that is why this is called as torsional strain. So any pair of tetrahedral carbon attached with each other to have their bond staggered for minimum repulsion between their bond, and any deviation from that staggered conformation are accomplished by the torsional strain. So you have to put torsional strain, then only you can reach to either of the other skew conformer or the eclipsed one, because everything wants to become stable, everything wants to become of least energy, and that is what this part is doing. This is called as torsional strain. Now I'll help you to write down the conformers of ethane. This is ethane, CH3, CH3. Let's say this is your front, this is your back. We have to keep front as fixed. Now anyone can be fixed, anyone can be rotated. So let us suppose I'm starting it from this. See, so front and back are in the with each other. So now change the dihedral angle with theta 60 degree. It will rotate the back one. Front is the fixed. Front will be the fixed one. The back one is rotated and come into the gaps of this. This is called as eclipsed. This is called as staggered. Then again apply this angle theta, again next 60 degree. For next 60 degree it will become what? Hydrogen, 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 and then it will become the same only right behind each other. This is again eclipsed. Once you go next for next 60 degree, the same will happen. Front will be kept constant, rear will be rotated, then again it will come to the gaps and it will become staggered. Note this thing down. Try writing everything by your own so that you will become very comfortable. Then we have the rotational energy barrier, is also known as conformational energy. The rotation energy barrier is known as the conformational energy, like rotating from the most stable to most unstable. It is the potential energy difference between the most stable and the most unstable. So between the staggered and eclipsed, the difference between the eclipsed and staggered is called as the conformational energy. And for an example, the conformational energy over here is, in ethane it is written conformational energy. Now we'll have some questions. The correct statement regarding the comparison of staggered and eclipsed conformation of ethane is: the staggered conformation of ethane is more stable than the eclipsed. Staggered has no torsion strain. I think this is correct. The staggered conformation of ethane is less stable. No. Eclipsed conformation of ethane more. No. Eclipse is more. No. I think A is the correct answer first. Next is, with respect to the conformers of ethane, what is possibly true? Both bond and bond length change. No bond length changes in conformational isomerism and no bond angle changes. The only change is between the relative positions, due to which their potential energy may differ. It could be acquire least potential energy with the most stable conformer, or can have even more. And whatever we are discussing, these are the projections in which we can watch this part, even we can observe this part, that two groups can have relative different position relatively, but else There is no change in bond angle and bond length in the conformational isomerism. Remains same, that is what I'm saying. So there comes the conformers of butane. Next is the conformers of butane. So guys, butane. First, let me just write the structure of butane. This is your butane CH3, CH2, CH2 and CH3. So take this as front and this as back, because that will give you a different conformation. Otherwise it will be like the same only which we studied. Staggered and eclipse will be becoming front and back. So front and back. Now let me draw the structures. This is your CH3 group for front carbon, hydrogen and hydrogen. Then coming to the rear carbon, we have CH3, we have hydrogen and we have hydrogen. This structure is called as fully eclipsed. Fully eclipsed. We will go for a 60-degree rotation in angle, bond angle. What structure do we get? This will remain constant, will not change. CH3H and H. And the rear one goes in here, in the gap. This form is called as gauche form. Gauche. I will go for another 60-degree rotation. Then it will form this structure. This structure is called as partially eclipsed. Then we'll go for another 60-degree rotation. This is fixed, not changing. And what about the rear one? That comes exactly opposite to it. So does these hydrogen in the gap. This form is called as anti. So after this anti form, go for another theta equals to 60. If you go for theta equals to 60, then it will somehow look like this. Front, not front. Front is the fix only, and rear will be changed with its positions. What is it? H, H, H. So it will come like this. This is called as partial eclipsed. Then again it will go for some gauche and will return back to the, because it will be 360 degree will happen, no? 60, 60, 60, 60, 60, and then theta goes to 60, it will come to the same eclipse. So this is what, these are the conformational isomers of butane. Hopefully this part is absolutely clear to all of us. This is the energy profile, guys. So most energy is acquired by the total eclipsed, fully eclipsed. Least energy is acquired by the anti form. But this only works up to wherever there are two bulky groups are there, or such simple cases. Whenever there is a case where hydrogen bonding can take place between two groups present at the butane, in that case, if there are like two, there is no, I don't think there is a required to understand it. This is the case if any of the atom present on the this side is either out of these, this will create a hydrogen bonding and will become more stable. See, any of these group, OH group, NH2, FNR2, NO2, COH, CHO, or one could be fluorine, another could be two fluorines are not there, one fluorine, another could be COH or anything. Then in that way gauche becomes more stable than even NT. So this gauche is more stable. Now try this question. These two conformers exist in the state of dynamic equilibrium. Which one of them is more stable? So this is very simple. This is an anti form and this one is the not anti-R. This is a staggered. This is eclipsed. And we know eclipsed has more torsional strain. So first is more stable, simply. Then we have which of the following molecule gauche form is more stable than NT? Gauche can be stable in NT only in the case of H bonding. So which we can see everywhere. D is the correct answer. Then we have angular strain, another important topic. I will come back and join you very soon. Let me bring my water with me and then we'll connect from here, okay? Yes, everyone. So now let's move forward from here. So did you guys go through it? This is what we call as angular strain. We'll study from here. What is the meaning of angular strain? Actually, our next target is to reach out to the conformational isomerism of conformers of cyclohexane. So that is why I came with this topic. So we call it Bayer strain. It's very simple. We call it Bayer strain. We also call it Bayer's angular strain. The formula is theta minus 109 degree 28 minute more divided by 2. So this is the formula of calculation of the angular strain. We all know that every single carbon atom over here, every carbon atom, right? Every carbon atom which you see is sp3 hybridized. And a sp3 hybridized carbon atom want to stay there or want to basically maintain a bond angle of 109 degree 28 minute for its stability, for its regular geometry. But 109 degree 28 minute is not possible here. And because it is not possible here, bond angle is just 60 degree. This is just 60 degree. So this is causing a cyclic or this angular strain here, and due to this strain, this makes the given molecule unstable. So let us just check which one of them has how much of this angular strain, and then we'll come to know. So guys, let's say if I talk about cyclopropane, the angle over here inside this angle theta is 60 degree. We know that geometrical angle, okay, this is the geometrical angle, geometry angle is theta. Now we have the hybridization angle. (109 degree 25 minute), so we can take it 109.5 degree, let's say, nearly. Here you will find the Bayer strain. Or angular strain which we are talking about. So number one is cycloalkane. Cyclopropane has a geometry angle of 60 degree. So this will become 100 okay, this is always 109 degree 28 minute. Bayer strain will be how much? 109.5 minus 60 divided by 5. So how much does it come? Because we are taking the mode, that's why we are doing it. So it will come up as 39.5 by 2. 39 is your 19 point. 75 degree nearly. Then we have cyclobutane, cyclopentane, cyclohexane. So try this everyone. This is 90 degree. So how much is this theta? 190. This will be 190, 28 minute only. The difference will be mod of theta minus 109 degree, 109.5 degree upon 2. So this will come how much? 20. So 19.5. So half of 19.5 will be 9.75 degree. This is the Bayer strain. This is how much is this angle? If I make this angle, this will be 72. So 72 minus 180, 180 minus 72. 108 degree. This bond angle is 108. This is 109 degree, 28 minute. So definitely it seems like that this is the least value of strain which we'll be getting, which is just 1.5. So this is 0.75 degree more or less. This is 120 degree. So 109, it will be 10.5 by 2, so 5.25 degree. So guys, what do you observe from this data? Data shows that maximum Bayer strain is here for propane and minimum should be for this, isn't it? Minimum it is still looking like for this. It seems like this is the real hero, but believe me, it is not like this. So now what we'll do, but actually cyclohexane has zero angular strain. Now, this is very unique thing which we are discussing now. It has zero angular strain. How? Because cyclohexane doesn't exist like the shape which have been shown here. Cyclohexane doesn't exists planar. Instead, it mainly exists in the form of chair form. It mainly exists in the chair form, where every bond angle is already 109 degree, 28 minute, and thus the angular strain comes 109 degree 28 minute minus 109 degree 28 minute by 2 is equals to 0. Now check this thing, very beautiful thing. So actually cyclohexane is supposed to have the minimum, and that's why always remember this part everyone. That's why 6-membered rings are the most stable because they do not have angular strain. That's why they are supposed to be the most stable. I hope this part is absolutely clear to all of you. So what are its basically these are whatever you are watching, these all are called as the cyclic conformer of cyclohexane. Conformer of cyclohexane. Let me just write their name. What do we name them? This is called as the lowest energy form is called as chair form. I'll write simply chair. The next higher energy is in the twisted bot. This is called as twisted bot. That is how it look like. The next higher energy is shown by the bot form. And highest energy is exhibited by the half chair, which is highly unstable. So chair is more stable, half chair is highly unstable. Half chair. Fine, everyone. So we won't go in too much of detail of these. It's like these are the like there could be several number of conformers which may exist by this cyclohexane, but the only important ones are these four: chair, half chair, bot, twisted bot. That is what we have to learn. We must know their energy order also, and then right after that we will learn one more part and then we'll leave this. The one more part is flagpole interaction that happens in the form of bot form. This is what bot form, and that makes bot form unstable than the chair form because there happens the flagpole interaction between these hydrogen and which repel each other. They repel each other. Conformational substituted cyclohexane. Cyclohexane keeps on doing the flipping. So what happens in flipping? It's very simple. First of all, I must tell you what a cyclohexane actually look like. Let me see first how does it look like. Okay. My drawing is not so good. Sorry for this. Like this. This is your bot form actually. Bot form can be represented by two ways. Both of the ways are correct only. Either you make it this, right? Both are the same only. This or this. Both are the same only. There's only a difference of view. Where are you watching it from? If you watch it from a bit top of it, then it will look like this. So guys, what is happening here? This is one form that we can see. The bonds I'm right now making are called as axial bond. So I'll write down A, and A. These are called as axial bonds. So these are axial and these are called as equatorial bonds, E, and no doubt E, E, wait, like that, E. Then this will also have E. So whatever you are seeing, E are the equatorial. No, this is not correct. This is actually equatorial. This is correct. So now guys, we must understand there are like two hydrogens. A is the axial hydrogen, and the E is called as the equatorial hydrogen. Right. So this is how the structure look like. Now it can undergo flipping. So what is happening in flipping? Let me first read it. What is happening in flipping? No, it will not go under flipping. The flipping happens whenever any of the group is substituted by, let's say now, any group substituted by any hydrogen substituted by any group. Okay, so let us say I am substituting this one with methyl. So how would it look like? The same structure. Yeah, drawings are like this. So if let us say I am replacing this part with methyl CH3, and rest others are the same only. See, hydrogen, okay, I forgot for this. Hydrogen, or not E, I wrote it here E. So is it missing anywhere? Like this. Jar. Fine. Rest all the groups are as it is, as they were earlier. Hydrogen, axial, everything is the same. So guys, we must know that which position has the more strain or more repulsion. So axial positions have higher repulsion and equatorial has lesser repulsion. So what we should do, because of these three groups, this are coming aligning with each other and causing more repulsion. This is also having a repulsion between these groups. This is repulsion, steric repulsion between these two groups. They all are coming all together. So what we need to do is we are not doing anything, flipping happens. See, this is ring flipping, and flipping happens automatically by its own. This flipping happens eventually by its own, and like whatever it was there on equatorial goes on like that. Okay, so this is how it will go. It is called as flipping. Flipping means, let me write it. What happens in flipping? Flipping of cyclohexane, mainly in this chair form. Flipping means all axial goes to equatorial and equatorial goes to axial, right? So now you will see the same group will come over here and the structure will somehow look like this. This methyl group has come to equatorial position now. Let me write this. Methyl group has come to this CH3, and now everything will be changed from here. This will become, the green one will become this, come here. Hydrogen. Hydrogen, hydrogen, hydrogen. Now equatorial, one were the green one earlier, they all go to the axial part. This is hydrogen, this is also hydrogen. See, rest others will come to the equatorial position. Which hydrogen? This hydrogen and this hydrogen, not this one, this one. Leave this. Like this. This is called as sweeping. Now you just observe this part and then I'll re-explain this part to you. First you observe this, and this is very easy, and I'll tell you my trick how I utilize to, how I manage to basically get these things. So guys, what happens, this is like up down is there, and alternate up and downs you can see. CH3 is up then down, so one axial is up, next is axial is down, up down. In a similar way, this also worked like this. This was down, this is up, this is down, this is up, this is down, this is up. See, one more thing is there. I always use one more technique. This technique says that leave one bond in equatorial and follow the another bond. Let's say this is the one, so you leave this bond, follow this bond, so it will be planar to that. So see, this is like this. This is how it is made. So anyways, this flipping keeps on happening 10 to the power 5 times per second, which is like a very big number. So the reason behind the flipping is no group is stable in the axial position. Group wants to come to the equatorial position. See, this is more stable. So let me write this. This is more stable. Now this structure is more stable. This structure is less stable. We'll directly solve some questions now on the application of what I just taught you. Which of the most stable conformer among given? So guys, we know that this is the group and this is what? Axial. This is what? Equatorial. This is what? Axial. And this is equatorial. Now this part equatorial, axial, axial, equatorial. Both equatorial will be more stable. Anything which is present in, and because in equatorial also they are like opposite to each other. Up down like that. Try one more question. Which of the following will be the most stable conformer and among the given conformer? Tell me. Very simple, everyone. Very simple. we have to pick that one in which both of the groups are in the no. Yes, here they might be equatorial and equatorial positions, but here what will happen, this does a intermolecular hydrogen bonding forming the 6-membered ring which is more stable. This is correct answer, D. Just because of the hydrogen bonding, D is correct answer. Now we have ended with the conformational isomerism and structural isomerism, and the only remaining part is geometrical and optical. So we'll quickly go through geometrical and optical also, and we'll finish the entire isomerism today. Let's go. So condition to show geometrical isomerism is there should be a geometric center. Now this geometrical center can be a double bond, or it's a cycle, or it's a multiple double bond. So many things can be thought, etc. I'm writing. Later on I'll explain what are they. Then different groups at restricted center. So these are the restricted sites. Whenever like let's say these are two carbon atoms, so these are called as the restricted sites because there is where we are having the restricted rotation. Different groups should be there. Okay, so like take this example. If we choose this example, let's say A is there. So guys, if A is there, even if you change the positions of A, it will not make any, so no GI. So I'll just simply cross it. Then if A is connected here, AB is connected here. Even if you switch it, A you switch them, A will be adjacent to A will be adjacent to B. This will not create any change. There should be entirely different groups present on two restricted sites. Otherwise, it will not show you any GI. But look at this. A in front of A, then A will come in diagonally opposite to A. This will show you GI. Then this is A opposite to A, B, yes, GI. Yes, GI. Even there are like all different groups, then also it shows you GI. Yes, GI. Yes, GI. So let us first read out. This is a kind of stereoisomerism which arises due to the restricted rotation of the groups up to a double bond or a cyclic system or whatever the system is there of the restricted rotation. So first of all, we must understand, guys, what is the meaning of restricted rotation. So restricted rotation means this. Let us say this is an alkene. So alkene has sp2 hybridized bond, right? Alkene, the doubly bonded carbon of alkene, we all know is what? sp2 hybridized. So let us just quickly get to it. So carbon has this connection between these, and due to which the sigma bonds of this are somewhere connected to, let us suppose this is A group, this is B group. Similarly here, B group, A group. So if you want to rotate it, let's say if I want to rotate this bond, keep one fixed, rotate another. Let us this is be fixed, and this we are rotating. So these are connected like this. Sigma can have a free rotation. Sigma rotation is called as free rotation. But pi rotation, whenever pi is formed up and down, it is called as restricted. Why restricted? Because tuck, it will once broken down. Now finger goes to thumb, another finger goes to thumb. So this will create two type of things. Rotation, if you do, and at what angle? Whenever this bond will be formed. So theta can only be 180 degree, and after this 180 degree, this will form Another geometry, because this is the fixed part, this will remain like this. This is the fixed part. This is sigma sigma free rotation, but free rotation is not possible because of the pi bond there. The B has reached here, A has come here, and the same pi bond has developed here. Like this. Now these two are called as the isomers to each other, and especially geometrical. We call wherever A or a similar group are in the same side to each other, adjacent to each other, we call that cis isomer, cis geometrical isomer, cis GI. And wherever there is a diagonally opposite to each other, it becomes trans GI, cis trans. Cis versus trans GI. So guys, cis and trans is pretty much clear to all of us. Cis butene, okay, butene will be, this is your butene. If it is cis, then we have to keep the similar groups in one side. See, similar groups comes in one side, then it becomes cis. If the similar groups goes in the opposite side to each other, then it becomes trans. It's that easy. Identify cis or trans. See, these two are in the same side of each other, and two hydrogen will also be, this is cis, this is like going opposite, this is trans. Two hydrogen will be here in the same side, this is again cis, and here the first one is cis, cis. Which of the following compound will show you geometrical isomerism? See, this question has been asked in JEE. Which of them will show you geometrical isomerism? Tell me. 2-methyl pentene. So let me draw 2-methyl pentene. No, there are like two same groups on this, it cannot show. 4-methyl pent-1-ene, 4-methyl pentene. This is correct, 4-methyl pentene. How? Let us check. Pentene and 1, 2, 3, 4 here is. So this is a one group, this is another group as hydrogen. So this will show, yes, different groups are there, no? This will show GI. Then in cyclic compound, what happens? So guys, I will explain you what happens in cyclic compound. Let us suppose this is the cycle. This is some cycle. And let's say there is a group A is there, or let's say this is A and this is B. And this is A and this is B. So, and they are like attached with this. But again, there is a restricted rotation, everyone. I told you, no. Why is it a restricted rotation? Because see, this is also bonded. So this will not allow it to freely rotate the bond. This is also bonded like this. So if you want to rotate this bond, what will happen? If you rotate this bond, this will be again how can I rotate this bond? Okay, this will be connected to this. One is connected to this. this lobe or this orbital, or another will be connected over here. So this is also a restricted rotation. So after rotation, what you get? This was the at once only. We fixed it. Now A will come to this position, B will be here. Then again it will become cis trans. Then let's say this is cis. Then this will become trans. Check it out. This is called as cis trans isomerism, geometrical isomerism. So you can use this, but remember this part of cyclic that only cycles only up to, not like that, a ring, or sorry, a double bond in cycle or a cyclic ring can't show GI due to no rotation. So guys, this is how it cannot work. If it is A, B, array yaar, this will not show any GI. Can't rotate. You cannot rotate it, and that is why it doesn't show you any GI. But the good news is, a ring with 8 carbon atoms or more containing a double bond can show GI. A ring that contains 8 carbon or more, that can show you GI, but below that it doesn't show GI. It has restricted, not restricted, it has no rotation. Instead I will simply write no rotation. Now there could be multiple things apart from cyclic compound. There could be more geometric centers, such as cumulene with odd number of pi electron. So guys, with 1, 2, 3, that is odd, double bond number is 3, odd. So what you will see, these are planar. This is the necessary condition, that they should be planar. These groups are planar, and you can check it. Cis trans is possible. But what happens in the case of, if there's an even number If let's say there is an even number, then they goes in the perpendicular plane A or B, and it doesn't show you GI. Let us take it, or let us accept it is directly only. Okay, don't just go very deep dive, otherwise you will get confused. Simply just adapt this part, that if there is an odd number of double bonds, then it will show you geometrical isomerism, else it will not show, because they go in the perpendicular plane. In the perpendicular plane we cannot judge which is in direction of what. So A will always be equidistant to A and B, that is why we cannot say that. We can also say that A will be equidistant to A in both the cases, cis and trans. So this is the correct one. The same happens in this pyrene also. See, 1, 2. So number of cyclic ring is even. How many rings can you see? 2 rings. So 2 rings are even, and that is why they goes out of the plane. See, this is planar, but this one is not. This is in perpendicular plane. So these two are in perpendicular plane, and in perpendicular plane no GI exists. You can't compare which one is in adjacent to each other, which one is diagonally opposite. Even if you change it, even if you do the restricted rotation, it will show you, it will give you the same identical compound, and they will not be no different to each other, and that's why we don't accept, and we always have to take these things into account. These things is in 1, 2, 3. This is odd number of rings are here. How many rings are here? Odd. Odd rings means 3 rings. Because right now these 3 are in same plane. They should be planar to judge whether which one is adjacent to which one and which one is going the opposite direction or diagonally opposite to each other. Same with cyclodines, means if let's say compound is here like this, so always make sure that the total number of rings, or whether it is the total number of double bond plus rings should be odd to keep A and B planar to another A and B. If it is not planar, then you cannot say geometrical isomerism will work. But if they are planar, then we can check whether they are like adjacent to each other or going diagonally opposite to each other, like that. There we end the geometrical isomerism in concept point of view. Yes, number of geometrical isomerism is less, that I'll tell you. Now let us solve some questions on geometrical isomerism. Here is the first question. Which of the following compound will give you cis-trans geometrical isomerism? Which of the following compound will give you cis-trans geometrical isomerism? What do you think? Which gives you cis-trans geometrical isomerism? 1 butanol. Butanol doesn't give. 2 butene will give, obviously. Very easy question. JEE Main 2021. Which of the following does not show stereoisomerism? Which of the following does not show? So let us check. 3,4 dimethylhexene. So 1, 2, 3, 4, 5, 6. 1, 2, 3. 2, 3, 4. So 3, 4 dimethylhexene. So it shows you GI. It shows GI. Then 3 methylhexavanine. 3 methyl and hex 1 ene. So yes, it will not show anything, but let us check whether any this is a star, so chiral center is there. It will show you optical isomerism. It will show you D plus L form, dextro-rotatory plus levo-rotatory. So this is incorrect. Again, this is also showing. Then we have ethyl hex 3 ene. Ethyl hex 3 ene. 1, 2, 3, 3 ene and 3 ethyl. This is showing GI. different groups are there, and 4-methyl hex 1-ene, 4-methyl hex 1 2 3 4 5 है 4-methyl 1 2 3 4-methyl hex 1-ene. So 4-methyl hex 1-ene, 4-methyl 3-ethyl hex 3-ene has what? Okay, this is incorrect, guys. This is 3-ethyl. So this is same groups are here, so we can say no GI. C is correct, because here again it will get a optical isomers. So about the geometrical isomer, we have these things remaining and we will cover these part. One of them is CIP rules, chain in gold prelog rule, to decide the priority of order, and then we'll come to EZ naming, EZ geometrical isomerism, then number of geometrical isomerism, and then geometrical isomerism will be over. Then we'll see whether we'll be continuing with optical or we'll cover this part in next lecture. So CIP is like chain in gold prelog. 3 scientists were there who proposed this rule. What is this rule? It's very simple, that if higher is the mass or atomic number, higher atomic number will be given as higher priority while deciding. How are we talking about the priority, everyone? So let us suppose this is carbon, double bond carbon, one is hydrogen, one is CH3, and one is C2H5, and another one is deuterium. So now check it out, everyone. Deuterium, C2H4, carbon has higher atomic number, higher atomic mass as well. This will be first priority, this will become second priority. This is first priority CH3, this is become second priority. Since 1 and 1 are opposite to each other, first priority is opposite, it becomes E isomer, E geometrical isomer, like that. So number 2 is, example 2 is OHSHI. If let us suppose, so first will be iodine here, first will be like if this kind of order is here, then iodine will be given priority over bromine, chlorine and fluorine. Here iodine will be given priority over SH, and then comes OH. Let us suppose if isotopic form is there, then the higher mass will be given as priority. So deuterium will be having more priority than tritium and even protium. If first atom is common, then you have to check for the second one. Let's say this first is carbon and second is carbon here. So this is coming Cl. Okay, what is it, by the way? I'm not getting it. Okay, iodine is there, no? So iodine is there. So I think B is most prior. Then we have C. Then we have D, and then comes A. This is the priority order. Check it out. If there is double bond, everyone, then double bond has to count 2 times, single bond has to count one time only. Just like if double bond is there, let's suppose double bond is there, then we have to consider this thing as let's say, and this will be considered as 2 bonds are already there, one another, like that we have to treat it. Similarly, if something is connected to triple bond, then we have to consider it as like this. But in case, let us suppose in one case, if let's say if we have to compare between these two, then this will given as priority is double bond, O is double bond O, but this is OH. O is the extra one which is here. It is connected directly to oxygen. This is connected to 2 oxygen to oxygen. This is connected to 3 oxygen total. And over here also iodine, because carbon is directly related to iodine. This might be connected to 3 nitrogen, but iodine is dominant. Even if it is one atom which is more dominant in atomic number than the rest one, then it will become most prior. Real structures will be given more priority than the virtual one. Virtual means if triple bond is there, we can consider this thing as CCC, but still this will be given as the priority. And out of these also this will be given as a priority. So correct order should be A, C, B. Now find the priority in each structure. This is the carbon atom. So carbon atom is connected to this carbon first, then oxygen one, and then carbon. This carbon is connected to oxygen. Okay, and then all carbons are there. I think this is most prior because this is the second atom is carbon. Carbon first atom is carbon. Second atom is oxygen. There is no oxygen. Try to arrange these things in the CIP order. CIP rule, follow the CIP rule and find out the order. So O directly oxygen is connected, will be given more, then COH, then CHO, and then CH2OH. COH, COH, this is the correct answer, B. Find the priority order. Priority, let me write 1, 2, 3, 4. Check it out. Then we have EZ. EZ, as I told you, very easy. The higher priority are in the same side. We call them Z. Zusammen means same side. Zusammen means same side. And if higher priorities are in opposite sides, we call it antigenal, means opposite sides. Okay, now simple nomenclature. Take this example, everyone. Let us say this is carbon double carbon, this is fluorine, this is bromine, this is iodine, this is, let's say, chlorine. We all know the most prior, this is prior 1, here the prior is 1, these are opposite, this will become E. That's how you have to decide, E or Z. So E or Z, what about it? No, deuterium is 1, here this will be 1, 1 and 1 opposite, E. Try these questions with me. So hydrogen are in same direction, so it will be cis also. First of all, it will be cis, then more priority, one is here, another priority, one is here, same side, it will be cis and it will be Z. Coming to C, fluorine and these are opposites, it is a trans. Most priority is this, most priority is this, opposite to each other, trans and E. Hydrogen are in same side, no, opposite to each other, so it is a trans. This group and this group are the most priority, number 1 and number 1. Number 1 are opposite to each other. This will be E, trans and E. It's not mandatory that E will always be trans. Always believe me, it's not mandatory that E is equals to trans. No, E can be cis also, and a trans can be Z also. Well, show you some example. Here more priority group is chlorine, here more priority group is this. Now these two groups are coming in same side, so this is Z. Also the hydrogen are in the same side, which means this is cis and Z. Taking this example, similar groups are these, same groups are this, so definitely this is a cis, but most priority group is this, another priority group is this, so these are coming down. Now cis and E it has become. So cis doesn't mean that it will, I don't know why it is irritating me unnecessarily. This will become cis and Z, not Z yaar, E, cis and E. So like that. If something is not having anything in common, then we are not supposed to write cis trans, only EZ will be written down. One carbon, then we have carbon added to carbon, next atom is fluorine. Here carbon, then chlorine. So fluorine is coming faster, fluorine is coming in a lesser number. This is priority number 1. Here this is priority number 1. This will become E. Rest you will do by your own. This is also I can explain. Priority 1. Here carbon. Here it is carbon. 2, 3 carbons are ones. This is carbon and then carbon. Wait, let me check. This carbon is connected to another carbon, then Cl, but this carbon is directly connected to two carbons directly. I think this will be the priority. I think Z is the correct answer. Rest you try it by your own. The IUPAC name of this. Now we all see these are what? The mainly group is this, this, this and this. So what should I say? This is Z and this is E and this is also Z. So Z is Z. C. Now this is a homework for you. You do it. This is another homework for you. Now we have number of geometrical isomers. That is very easy one. So number of geometrical isomers in case of unsymmetrical alkene is given. Unsymmetrical alkene means left and right side are not the same along with this alkene. Or you can do one thing, go from left side or go from right side and give the number to positions plus IUPAC nomenclature. After giving the number from both sides, if comes same, then we call it symmetric, and if it comes different, then we call it unsymmetric. Clear? If it is a symmetrical alkene, then we have two cases. One of them is this n-1 to the power n-1 and then n by 2 minus 1, where n is actually even, and if this n is odd, then becomes n plus 1 by 2. Anyways, this is something that you learn directly, and this is actually we have covered till here up to, what should I call it, what we are discussing right now about the alkenes and all. This is mathematically calculated, so we can directly adapt the formula in order to find out the number of GIs. I'll show you some of the beautiful examples related to the same, but you better learn it as of now. I think geometrical isomerism is something that we'll cover till today. Optical will be covered, I guess, later. Or let's see. Yes, so learn the formula. Now it's time to solve some questions. First of all, let us check out whether it is a symmetric or asymmetric. Symmetric has a similar ends, like whether you want to start it numbering from left side, right side, everything will come on the same number. See 1 2, there also 1 2 3 4, 1 2 3 4, everything is same. This is a symmetric one. You can name also IUPAC name from left and right and you will find the same name after numbering from left and right. Symmetric alkene. So for symmetric alkene we know the formula. So what is the formula? 2 to the power n. And what is the number of n? Number of geometric center? 1 2 3. So 2 to the power 3 minus 1 plus 2 to the power 3 plus 1 by 2. So what does it become? 2 to the power 2 plus 2 to the power 2. 4 plus 4. I think 8 is the correct answer. What is wrong with me, yaar? Okay, that is minus 1. N by 2 minus 1. Okay, my bad. This is 2 to the power n minus 1 by 2. Not like that. 2 to the power n by 2 minus 1. अरे no यार, n plus 1 by 2 minus 1. Okay, got it. 2 to the power n plus 1 by 2 minus 1. So this will become 1. This will become 6, like that. Then we have properties of geometrical isomerism. Properties are very similar, everyone. Melting point. Melting point is directly proportional to the packing of molecules. So which one has the better packing? This has the better packing. That is why cis has lesser melting point than an extent of packing. The very good packing is present in. Done. Then we have boiling point. Cis has more boiling point because boiling point is directly proportional to the dipole moment. And dipole moment will definitely be higher for cis one. Trans has almost 0. Solubility of cis will be more than trans, and solubility we are talking about in water. Then dipole moment will be higher for cis only, as we have checked here. Dipole moment it is asking, so this will be having 0. And this will also, cis will be having higher. Fluorine is cancelled out, this will have higher. Then this is the only way where cis is not having the higher, or the cis trans is there. And see, this is giving there, this side. Chlorine is accepting this side, they will be added. Here this will be in this side and this will be in this side. This is like subtracted, so I think this will be having more dipole moment. Next we have optical isomerism, that will cover later on. Let me see if we have the time. Anyways, right after a break we'll start. You better revise it till here. So we are now having a 15-minute break time. The only part which is left is the optical isomerism. So just stay tuned. So guys, that was some healthy break we had, and thank you for being so patient. I hope you all have done with your dinner, because I also went for the same but couldn't find it. But anyways, not so hungry. I had some snacks. So now we'll continue from here, and I have only one topic left for the day. And now this is our task. We all will be sitting more focused, more consciously, writing down what major points are about, because this topic is now, it is from 12th standard. I have taught you complete part of 11th standard isomerism, which was structural isomerism, conformational isomerism, and then we had geometrical. We have completed all three parts in very detail, very neatly, and with very good examples and PYQs. Now we have this optical isomerism. So let me just start. What is the meaning of optical isomerism? So I will give you this idea, guys. First of all, what is the exact meaning of optical isomerism? So they don't look like different. Okay, first of all, their structure is entirely same. The position of the atoms, everything is absolutely same. But what they exactly different in? There some of the properties are different, and mostly their physical properties are different. Their chemical properties might also be different. What actually happens? Try to understand it. We have a light, we call it plane polarized light, which has its particles vibrating in the same plane. Whenever this plane polarized light is passed through one of the optically active compound, we have seen that the path of this light is deflected at some angle, whether it is deflecting in the clockwise direction or anti-clockwise direction. On the basis of that, we have named this compound as dextrorotatory, which can rotate the incoming path of plane polarized light into clockwise direction, and another one could be levorotatory, which can rotate the path of plane polarized light into anti-clock direction. So based upon that, we have levorotatory and dextrorotatory. So that is what we call the optical activity. Now to decide which compound should be optically active and which one should not, based upon its structure, we have plenty of criterias. So I think now I have given you the proper parameter related to the optical isomerism, and now we should cover every single part. So isomers with similar structure and mostly the similar properties, the only difference in the behavior towards the plane polarized light. As I told you, the type of isomer is called as optical, and a molecule can rotate the plane polarized light is called as an optically active compound or optically active molecule. This property is called as optical activity. So that's how it is defined, that polarimeter is the tube which is used to detect or the measure the amount of deviation of the angle of that particular light. So polarimeter tube contains an optically active substance such as amino acid in a solution which causes the plane polarized light to rotate. So this is how it works. This is a general framework which you can see. A general framework decides that when an ordinary light which has light vectors or the particle rotating in every direction, they all comes and start doing the vibration in the same plane, and it becomes a polarized light, or we call it plane polarized light. This plane polarized light, when passes through organic compound, has two type of possibility: either to get rotated in the clockwise direction or to get into anti-clockwise direction. The clockwise basically clockwise rotation is termed as the dextrorotatory. Dextrorotatory is the nature of that compound, represented by small d, or it could be negative or levorotatory, that means which is rotate towards the anti-clock direction. Now we must know what is the optical rotation theta or alpha. So optical rotation theta is actually the angle at which it is rotated by. The angle through which a compound rotates the plane polarized light is called as the optical rotation. It's very simple. We can also calculate the value of theta using this formula of alpha. So alpha is called as the specific rotation. Alpha is called as specific rotation, and it is equals to the observed angle, which is theta, divided by the length of the polarimeter tube. So it will give you that for 1 centimeter of the length, 1 centimeter of the length, how much is the change in angle of the plane polarized light? That is what we call as the specific rotation, and it is defined for 1 decimeter, sorry, not 1 centimeter, it was 1 decimeter, 10 to the power minus 1 meter in length, at a concentration of 1 gram per ml. We are maintaining a concentration of 1 gram per ml for that particular optically active compound. The amount of rotation depends upon the wavelength of the beam which is coming, temperature, density, length of the polarimeter tube, and then the nature of the substance. We have applications. Specific rotation is used like a fingerprint to identify the compound. It is also used to distinguish between D and L isomers form, such as this example. Guys, this is called as Fisher projection. We till now have covered so many projections such as Sohor's projection, Newman projection. This part is remaining that I will right now explaining to you, called as Fisher projection. And Fisher projection is exactly like the others, but a bit different, and it is given only for those compounds which are optically active, which have the chiral center in them. Anyways, first of all, the application of optical rotation, I will tell you that this is called as D-lactic acid. D-lactic acid is having OH group in left hand side and L-lactic acid is having in right hand side. It can rotate the plane polarized light by minus 2.67 degree and can rotate by positive 2.67 degree. So can you imagine this part, that only the position of two groups whenever interchanged or exchanged, it can rotate the plane polarized light by opposite angles. So this is what the importance of optical activity is. It is used to identify the nature of compound. Now, on which of the following condition the specific rotation doesn't depend? It depends upon temperature, concentration, wavelength of light, but it doesn't depend how much light we are passing. Intensity of light doesn't depend upon. Now we have elements of symmetry. So guys, wherever you find the element of symmetry, a molecule which contains any of the element of symmetry is always optically inactive. So always remember this part: to be optically active, a molecule must be chiral or asymmetric, and it must not contain any of the center of symmetry or plane of symmetry. It must not contain. Axis of symmetry is a different thing. This can be exhibited by anyone, but there is one more thing called as alternate axis of symmetry. So some compound which has alternate axis of symmetry, it can never be optically active. A compound can be optically active even if it is having the axis of symmetry, because axis of symmetry doesn't have that significance. Axis of symmetry is a different thing. It shows you that by what kind of rotation an imaginary axis passes through a molecule, and at a particular angle the molecule acquires again the same shape or the same configuration. That is what a different thing is. Now we'll come to center of symmetry, plane of symmetry, and axis of symmetry. Very fast we'll go because we already have covered this part till here, and some of the points are very much clear to all of us. We know that if you cut this thing, if you cut it in the two equal halves, which two are exactly the mirror images of each other, then this is called as plane of symmetry. This plane is called as the plane of symmetry. Next is, we have, okay, plane of symmetry, the same part is here. Always make sure that this is set to have the plane of symmetry, but this cannot be considered as the plane of symmetry. What if I cut? No, if I cut it low, no, there is no plane in which we can cut to get the plane of symmetry. This contains no POS. Then we have center of symmetry. Center of symmetry is a point present inside the structure or the molecule, from which if you draw a line and that passes through the center of symmetry, it has an equal distance from the one where it is started and from the one where it ends. What is the point? What is the meaning of that? If you measure this distance between two pH atoms, this length is L, this length is also L. That is what it says. Axis of symmetry, very easy to explain. That axis of symmetry is an imaginary axis is there, and if you rotate a molecule by certain number of angle, the molecule again acquires the original structure from which we started rotating it. So these three are some elements of symmetry. Now we have chirality. Chirality means the property of being asymmetric. The object which are chiral are supposed to have non-superimposable mirror images. If you put this P, this inverted P over this P, it will not superimpose it. It will be non-superimposable. That is why these two structures are said to be chiral. Mistakenly came here. Then we have chiral carbon. Has a chiral carbon, if we talk about, or chiral center if we talk about, is some atom with four different groups, minimum of 4 different groups is said to be a chiral atom, and these ABCD should be different to each other. So let us just take this example and let us try solving POS, COS in the given compound. So what I'm asking is, let's say this is a compound, and Let us say if it has a plane of symmetry, does it has a center of symmetry, and it is optically active or inactive. So look at this example. So how should I cut it? Not like that, not like that. I think this has no plane of symmetry, but center of symmetry is also not there because of BRCL. Is it optically active? Yes, it is a chiral molecule. Look at this example. It has a plane of symmetry. This could be the plane of symmetry. Center of symmetry is not there. If any of the element of symmetry among them is there, it will automatically become a chiral or symmetric molecule, or we can say optically inactive. Identify the asymmetric carbon. Asymmetric carbon is the one, or the chiral center is the one that contains 4 different groups. One is hydrogen here. This cannot be considered. This can be considered methyl group, bromyl group, this group, and hydrogen. Here, this group is different. This group is different. This is the chiral carbon. Here, 2 same groups are there. It cannot be, but this can be. And here, this cannot be. This nothing. If I take this, identical, okay, no, we don't have any chiral center there. So how many chiral centers can you see in this compound? Chiral center means those carbon atoms with 4 different groups of atoms. So one is this, and this cannot be, this cannot be, this, yes, that's it, 4. Which compound does not possess a plane of symmetry? What do you think doesn't possess a plane of symmetry? See, this is a plane of symmetry. Here, this can be the plane of symmetry. This doesn't have plane of symmetry. This doesn't have any plane of symmetry. This has a plane. No. Look at the structure. 1, 2, 1, 2, 3. No. What do you see? Does not possess a plane of symmetry. Third doesn't contain, 4 doesn't contain. Okay. Wait. 1, 2, 3, 4, 5, 6, 7. No, yeah, that doesn't contain plane of symmetry. No, it contains a plane of symmetry. Does it? Guys, cut it like this. Then it has plane of symmetry. So I think 3 and 4 can be the correct answer. D. Which of the following would show optical isomerism? Optical isomerism with chiral center. Okay, that's it. That is the correct answer. Which of the following can exist optically active forms? Which of them can exist in optically active form? So it has a plane of symmetry. This has no POS, no COS, and we know that this will be chiral, so this is correct. Optically active forms. I think that's it. What do you see? Now let me tell you what is the meaning of Fisher projection. Fisher projection is actually a 2-dimensional representation of a 3-dimensional stereo center. So how do we represent it? You always check wherever these two lines are meeting, that will be a chiral center. So how do we define it? See, how does it look like? Its actual presentation is, these vertical lines are coming towards us, so it somehow look like, no, not towards us, these are coming towards that vertical, horizontal one. So this is how it look like, and vertical ones are going inside. So this is CH2OH is going inside, CH3 is going inside, this is your OH, this is your H. That's how it look like. So horizontal line represents the projecting forward, and vertical line are going to the rear, and the only atom in the plane will be the stereo center, the one which is chiral carbon. The main carbon chain should be placed on the vertical line only. The most oxidized carbon atom, most oxidized means like COH, CHO, CH2OH, like that, will become at the top. So if the arrangement, it is the arrangement of the atoms or groups of that is described independently of the any other atom or group of atom in the molecule. This type of configuration is defined for the chiral molecular entities and stereochemical descriptions. So guys, there are two things that we use, R rectus and S sinisters, showing the, no idea on that, we'll come to that actually later on. So that's how we do it. Okay, RS configuration. Okay, let me just tell you what is RS configuration. It's very easy, everyone. So let us suppose this is your fourth priority group and it is coming on the vertical line. Hydrogen is least priority group, we all know. This is the fourth priority group. If it comes on the vertical line, then let's say this is 1, this is 2, this is 3, and rotate it 1, 2, 3. What is it showing you? Anti-clock. Anti-clock is called as S sinister, and capital R is rectus, that is clockwise. Getting me? Similarly, here fourth priority group is at okay, where is 1? This is 1, this is 2, this is 3. So 1, 2, 3, it is clockwise. Clockwise is called as R. Anti-clockwise 1, 2, 3 is called as S sinister. Similarly, if your one of the fourth priority group is on horizontal, if it comes on the horizontal, so either you can do one thing, make even number of changes there and send this hydrogen at the end of this chain or the vertical part by doing the even number of changes. But if not, then opposite configuration will be followed. Clockwise will become S, anti-clockwise will become R. Now we have some examples. So guys, what are these examples? So let's say if we talk about this, this might not be looking like the way we want to see it. This is 1, this is 2, and the lower part is actually 3. So 1, 2, 3 is clock, anti-clock, and this is on horizontal, so this will become R. And the same happens here. 1, this will be 1, this is 2, and this is 3. So 1, 2, 3. what is it coming? Anti-clock, so it will become also R. So this is RR configuration. This is RR configuration. This is an optically active compound, by the way. This compound is an optically active, and that is why it will be having a mirror image where both will be S and S. You can check it out. But if this compound is there where see, you can find a plane of symmetry is also there, POS. Such compound is called as a meso compound, and a meso compound has a superimposable mirror image. These two are identical. This is identical with the left one. You better try these things by your own. You practice it, and I will provide you the proper notes. Please follow my notes. Believe me or not, these notes are self-explanatory. You can just read it out once and you can get all the concepts done. So guys, if you make an odd number of changes, the configuration changes. R becomes S, S becomes R. But if you carry out even number of changes, R becomes again R, S becomes again S. Now we are doing the RS configuration for wedge dash, and this is again very easy. You follow my rule and then you will forget everything. You will become very confident. Right. This is 1, this is 2, this is 3. 1, 2, 3 is coming what? Clock becomes R. Then again 1, 2, 3 anti-clock. Anti-clock becomes S. But when this hydrogen is on dash position, or if it is not on dash position, then it should be directly opposite to the dash position, like one after one. Anyways, I'll come to that. But if it is not on the dash position and it is adjacent to the dash position, then see 1, 2, 3. This is what? 1, 2, 3 anti-clock. It will become R. But it will become R opposite to that. I'll give you one or two examples and then you will become very much comfortable. An absolute configuration of following molecule is what? Absolute configuration means RS configuration talking about. 1, 2, 3. What is 1, 2, 3? Anti-clock, but this is on, the anti-clock becomes R. So we'll call it 2R. See how easy is this? Arey yaar. 1, 2, 3. 1, 2, 3 is anti-clockwise. Anti-clockwise should be S, but hydrogen is there. This is, I am right, this is 2R. This cannot be 2S. I am absolutely correct. This is not correct. This is the correct answer. Correct. I am right. Okay, let me take you to this example. This will clarify all your doubts. COOCH3 and COH. One H is there right after carbon. There is a CH3, so definitely this will be the most priority one. This will be the second priority, and this will become the third priority. See, 1, 2, 3 is coming clock. So clock and hydrogen is where? On the vertical, the horizontal line. So it will become changed. So R becomes S. So 1 is the S. This will become S. Now coming here, this is already there. So whatever the rotation is there, that will be considered as the final answer. This is 1, this is 2, this is 3. So this is 1, 2, 3. What is coming? Clock R. So this correct answer is R. So S or R, C is the correct answer. Now see how come this is correct and the previous one is not. The previous one was given with the wrong answer, so I changed it. Then we will talk about some of the important terms, and since it's been long hours I'm standing here, now I'll sit a bit. Now we have some simple terms to discuss about, and we'll go a bit quickly from here. The very one of them is called as enantiomer. The meaning of enantiomers is non-superimposable mirror images. The optically active compounds which have a non-superimposable mirror image is called as non-superimposable, but it should be mirror image also, because meso compounds usually, if we talk about the anyways, but first take this compound. So R configuration will be S, RR will be SS. But if there is RS, that RS will be diastereomer. You cannot count RS as a enantiomer. Enantiomer should be mirror image, always a mirror image with non-superimposability. Then characteristics, yaar, let me go and sit there, yaar. I'm hiding some text. So characteristics are, they are identical in chemical and physical properties, and they have only differences of the towards the plane polarized light or these optically sensitive chemical reactions. Then only they can show the differences. Otherwise, then we have a meso compound. So guys, meso compound, whenever it is obtained, usually whenever in a molecule two type of chiral centers are there. One center has all three same groups, another center has all three same groups, and one is the common linkage between these two. In that way, there's a possibility one could be R, another could be S. In that way, they will definitely be having a plane of symmetry in them, and such compound become meso compound. Now if you compare this SR configuration with the SS and RR, we recently discovered RR and SS were the enantiomer. Then what is the relation of these compound with this SR, meso? Meso is said to be the diastereomer of rest of these two. Just like both of them were enantiomer to each other, meso compound will become a diastereomer of rest two. Very simple, yaar, not a problem, yaar. And then also if there like more than like one stereo center is there, and one could be changed, another could be the same, like RR, this become SR. This also is a meso compound because that is not a mirror image. See, not a mirror image. Then it becomes diastereomer. Characteristic of diastereomer: diastereomers may have different physical properties such as melting point, boiling point, density, solubilities, and value of specific rotation. They can be separated from one another by physical means like fractional distillation, fractional crystallization, chromatography. Geometrical isomers are also diastereomer. Oh great, geometrical isomers are said to be the diastereomer of each other. I will learn that part. Let me check how much of this chapter is left from here. Okay. So guys, now we'll come to another important part of this particular topic. Racemic mixture is a mixture in which both optically active forms are present, which are mirror images to each other. Like it's a mixture of enantiomers, then optically it becomes overall optically inactive, because ratio, if a racemic mixture contains both in equal proportion, both in equal number of moles, then it will be optically inactive. But individual component of a racemic mixture, DLN, are always optically active. Next, meso tartaric acid and D-tartaric acid are diastereomer. Very simple. Which pairs of the enantiomers are diastereomer from 1, 2 and 3? Guys, you need to check out. This is 1 and this is 2, not 2, this downward is 2, and this is 3. So 1, 2, 3 is coming anticlock S, but this is there, it will become R, and this will be 1, 2, 3. 1, 2, 3 is anticlock, but this again, this is RR. Guys, this is RR. So its mirror image is this, it will become SS, and then this will become what? RS. So guys, what do we see? Identify the pair of enantiomer. Enantiomer will be what? First and third. Diastereomer, first and third. First and second, and third and second. Very simple. Yeah. Now this part has become very easy to me after just going through, like revising the properly and going through the points. Now it has become very easy to me to explain or to basically identify which pair can do what. Which of the following pair of isomers can be separated by fractional crystallization? Fractional crystallization can be yes, diastereomers can be separated. Diastereomers. Then we have relative configuration. Relative configuration means a configuration apart from the RS configuration, just like DL, capital D, capital L. Very easy, everyone, very easy. you properly write down the Fisher projection, you reach to the final one, you reach to the final one and check whether OH group is in right or it is in left. If it is in right, it becomes capital D glucose. If it is in left, it becomes L glucose. It's very simple. See, right, it becomes D. If it is left, L. That's it. We over with this part. That is it. So now let me name this. Okay, right side, it's D configuration. That is how you make the mistake. It is incorrect. Dude, buddy, always try to make correct Fisher projection first. So let's say we are rotating it first, and no, we are supposed to send this up. Okay, so do one, then do second. So CH2OH should be sent to top. I told you, no, most oxidized carbon should be at the top. Then OH was as it is. Hydrogen first reached there, CH3 came here. No, first CH2OH came here, hydrogen reached here. Now CH2OH has reached to the top and CH3 will come here. But again, it is in the right hand side only. I think this D configuration is correct. We have another system called as erythro and trio. Believe me, it's another very easy. It happens only where there are two chiral centers, and in two chiral centers, when two things are in same side, if they are in same side, we call them trio. And if they are in opposite side, see, becomes, sorry, trio, sorry, erythro. Mistakenly we write, this is erythro. Erythro and trio. Erythro means opposite, same things are opposite, and erythro means, sorry, trio means opposite, erythro means same side. Where are the same side? See, this is the structure, Cl, not Cl, hydrogen, hydrogen are the same side, opposite. Erythro and trio, see, OH, no, first you need to convert them. So till then I can take this example, HH are in the same direction, and this will become erythro. We have to first make this compound accordingly. No, yaar, we don't need, yaar. See, trio. Assign the relative configuration to this. Relative configuration we need to assign. Okay, I'll do. So what we have to identify first of all? So we are supposed to check for the, this is the first carbon, second, third. For the final carbon only we have to check, and this comes into the left. So it will simply be L form. No need to discuss anything here. Just check for the last atom. All our homework, you try by your own. Chirality without chiral center. Chirality without chiral center means there could be some compounds in which we do not even require 4 different groups to be connected with yeast, and these we have already seen that earlier they were coming with the geometrical isomerism, where odd number of count was taken to make them same or planar, so that we can decide whether A is in the direction of A or opposite to it, cis trans. But now the one which we were ignoring by that time, where the total count will be even, where the number of alkenes or these spirines will be even, there they will go in different plane, and then they can also show mirror images to each other. Similar example could be this. Due to presence of a larger or bulky group at ortho positions of the biphenyl, it becomes planar at room temperature, non-planar at room temperature. True. That is why, see whether this following is this. Now how many? 1, 2. We can see number of, this is even. If any even number of allenes are there, continuous leans, this becomes optically active. But there should be different groups also. Oh, optically active, it is already optically active. wait yaar, wait. This cannot be optically active, dude, because it has a plane of symmetry. You can cut down this in this plane. So this will be, it will be cut down. Let's say this is this, and I am cutting down this into this plane. So because in order to that there should be different groups also, na? But this carbon has same groups, so it becomes optically inactive because it contains a plane of symmetry. This compound has a different group C, CH3Br, and this count is also even. Double bonds are even. This will be definitely, it doesn't have a plane of symmetry, it doesn't have a center of symmetry, it has optically active, non-superimposable mirror image. Which of the following is chiral? Which of the following is chiral? Same groups are there. This is this has a plane of symmetry, and this has no plane of symmetry. Different groups are there. This is become chiral. Second is chiral, only second. Finally, the last topic I would like to run. It's been a long time we have been teaching, so I would like to wind up our session here. So including today, I have finished complete GOC for complete 3 days challenge. I don't care whether how many people joined me, but I know that when people will come in future and they will watch our videos, they will definitely like the session and they will come to know how easily I explained all the most difficult part of chemistry in just 3 days, that is organic chemistry of 11th class GOC. And this is what we are dealing it with 12th class chemistry now. We need to calculate the number of optical isomers, and a similar kind of rules will be followed. Case 1, if it doesn't contain any plane of symmetry, and number of optically active compound will be 2 to the power n, number of mesoforms 0. If it doesn't contain any plane of symmetry, okay. Similarly, if a compound contains plane of symmetry, or if a compound is a symmetric compound, then optically active will be 2 to the power n, and mesoform will be 2 to the power n to the power minus 1, or total will become 2 to the power n minus 1 plus 2 to the power 2 by 2 minus 1. Even number. And if it is odd, then odd 2 to the power n minus 1 plus 2 to the power n minus 1 by 2. Overall, on adding, this becomes 2 to the power n minus 1 in total. So how many optical isomer does it have? 1 OH, 1 H. This is only 2. How many optical? 2 is the correct answer. Case 3 is already covered here, mistakenly pressed. How many optical are possible in a compound with 1 chiral carbon? Only 2. D plus L form in enantiomers. How many stereoisomers can be generally represented by this? 2 to the power 2 is equals to 4, because it's a non-symmetric, unsymmetric one. So now if you face any doubt, do let me know. Otherwise, I am winding off from this session. And if you want to ask me, you may ask your doubt. And if not, then I'll leave and we will wind up from here. Kamesh, you can ask me now. So I'll take your doubt. If you have any, just post me in the comment section.